everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 12 and we will be continuing with MOSFET IV, a brief part of it, and then shift to threshold voltage. What is the meaning of threshold voltage and definition of threshold voltage? In our previous lecture, we have actually been able to explain to you how ID will vary with respect to VDS for a varying values of VGS. We have seen two important points. For a fixed value of VGS, as the drain to source voltage increases, initially it is linear, and then when VDS exceeds or is equals to VGS minus VTH, and after that the current is almost constant independent of the value of VDS. Further, as the value of VGS also goes on increasing, since more and more inversion layer charges are available, the current also tends to increase, and that is shown by this graph here, right. That is shown by this graph here. This region is known as saturated region, and this region is referred to as a triode region of operation, right. And when VDS is very small, we define that to be as a deep triode. Now, if you therefore bias your MOSFET somewhere here or somewhere here by choosing an appropriate value of VGS and VDS, two things will happen. One is that its output resistance or output impedance will be infinitely large. Why? You see, how do you define output impedance? It is given as V by I, any voltage by current. But since the current variation del V, actually del V del I, now since the voltage variation at this particular point, if you look at the input impedance, since the current variation is 0, right, you are not varying any current, it is almost straight line. Therefore, the denominator goes to 0 and therefore Z tends to go to infinity, which means that if you bias your device at this region, the output impedance of the MOSFET will be relatively high. In fact, in ideal cases it will be tending to infinity. Now, the second point to be noted is therefore, but then it behaves like a very ideal current source. What is the meaning of ideal current source? Ideal current source tells me that irrespective of the bias or an external source, the current flowing from an ideal current source should be always constant, and that is what is happening here in this graph. If you look very carefully, for a fixed value of VGS, if you vary VDS, no current change is there, which means it is behaving like a ideal current source. So, if you want to make MOSFET as an ideal current source, try to bias it in this region. Do not make your VGS go very small. If the VGS value goes below the threshold voltage, you will have cutoff, and therefore the current will be almost 0. So, it will be very close to the IDS axis. So, the good region of operation is somewhere here where the device can work properly, right. So, this is the basic idea of a MOSFET ID-V characteristics. Let me now come to the threshold voltage concept, which I have already discussed, but nonetheless we will do a small threshold voltage concept. The concept of threshold voltage is defined as something like this. We will not take the root of the energy band diagram, but we will talk in terms of the number of charge carriers. Now, I define the threshold voltage as that minimum gate voltage at which the area or the volume just below silicon dioxide interface has got the same number of charges, electrons per unit volume as there were number of holes initially. You got the point? What was the methodology? Methodology was, if I have a MOS device and if I go on increasing the gate voltage, initially so it is an N-type MOSFET. So, my substrate is basically P, so number of holes are larger, the minority current carriers are N, and electrons are coming also from source drain region. I go on increasing the value of gate voltage, the positive P or the holes are getting reflected, or they are getting deflected down to the substrate, and what is left is basically the negative ion. You see, these are negative ion. What is the negative ion? These are fixed charges near the silicon dioxide interface. You further go on increasing the gate voltage, now you will be able to pull electrons from the substrate and N plus region of the source and drain, right. Though the depletion region will be larger in the source and drain region, but still, because the electric field will be larger, you will be able to pull large number of electrons. When you pull a large number of electrons, you will be forming a channel between N plus region. So the concept is that the interface is basically inverted. That's what is written here, right? And therefore it forms an inversion layer. So the value of Vg at which this phenomena happens is referred to as a threshold voltage, correct? And this threshold voltage is depending on many factors, we will come to that now, but typically the threshold voltage is defined in this manner. The definition can also be changed, or maybe the same definition can be kept even if you keep this to be as a 0 volt. So, I am not applying any drain voltage, I am only applying my gate voltage, and I am able to sustain the value of the threshold voltage in this manner. So, this threshold voltage is therefore there. So, for an N MOSFET, for an NMOS, since you will be applying a positive gate bias, right. So, my threshold voltage will be positive or greater than 0. Whereas, if you take PMOS, right, PMOS is basically having a substrate of N type. If it is an N type, you have to apply a negative bias at the gate side to pull the holes. So, for the PMOS, the threshold voltage will be negative, right, and that is what is all about. So, threshold voltage is basically that gate to source voltage. So, always with respect to source, we are saying it to be negative, which means that let us assume that the source is grounded, then my gate voltage will always be negative in one direction, and they will form the channel here. Now, so that is what I have already told you in the previous slide, that in semiconductors we say that the threshold voltage is that value when it was as much N type as it was initially P type. For an enhancement mode N type MOSFET, we say that it is becoming as much N type as the substrate was initially P type, correct. So, it was initially P type, and that is the reason it is referred to as an inverted region. So, it just get inverted from P type to N type. Now, the threshold voltage is comprising of 3 terms, right, primarily. Other variations will come when we go to cryo, but if you look at the threshold voltage modeling, 3 terms comes into picture. The first one is phi ms, which is basically the work function difference between the metal and the silicon substrate. Why are you saying between metal and silicon substrate? Because you see, if you go from the gate side towards the channel, phi ms has to be spent just to overcome the flat band difference or the work function difference between metal and semiconductor. So, this will surely come, and you cannot miss this point. What you can do it, if you want to reduce the value of threshold voltage, then try to match the type of material with the type of silicon which you are using, such that the work function differences are reduced to the bare minimum. This is known as work function engineering in MOSFETs. And if you make the work function of metal very close to the work function of semiconductor, then the difference between them is approximately equals to 0. So, we define phi ms as phi m minus phi s, right. So, this is the first part. The second part is 2 phi f, you see 2 phi f, where phi f is the Fermi potential. Now, you see this is quite interesting. Why 2 phi f? Because you see you are inverting the channel, which means that when you are depleting the channel, you will have one Fermi drop available to you, and then you are inverting the channel, you have a second Fermi drop. So, if you add the 2 Fermi drops, that will be the total amount of voltage which has to be given to the gate side for an inversion to take place. So, that is the reason you define this as 2 phi f, right, where phi f is the Fermi potential available to us. Please understand, we are not talking anything about the difference between the Fermi level and the conduction band, no. I am assuming that the Fermi level, let us assume that Fermi level is very close to the conduction band, and if I have an N type semiconductor, then let me assume that this is my conduction band, this is my Fermi level which is very close. Now, if you, this is my interface, this is my MOS, this is the oxide layer, this is semiconductor, and then I have a metal here. So, just near the semiconductor, as you apply a positive gate bias, this will start to dip down. More is the dip, more charges will be accumulated. So, 1 phi f dip will make this semiconductor go into depletion mode. Second phi s dip will invert it. So, that is the reason you have 2 phi f, so the amount of potential is available to us. And the last part is Q depletion by Cox. What is Q depletion? Is the charge of the depletion region divided by Cox, right. Now, if you remember, Q equals to CV, so V equals to Q by C. Now, this is basically the amount of voltage required to deplete the channel, right, because it is Q depletion by Cox. So, amount of voltage required to deplete the channel. So, therefore, that overall threshold voltage of a bulk MOSFET, N channel MOSFET, and in this case N channel I am assuming, is the sum of 3 components, which is phi ms plus 2 phi f plus Q depletion by Cox. Now, in most of the devices community or those who are working with devices, they try to reduce the threshold voltage to the bare minimum. Why? Because you want the device to get switched on at a very low voltage, right? And that's a very logical way of thinking also, because if your device gets switched on at very low voltage, you don't have to spend large amount of voltage otherwise. You can spend a smaller amount of voltage, your power levels will be relatively changing. Now, the idea here is, if, as I discussed with you, if you keep phi m and phi s almost equal to each other, obviously phi ms will be small, but that is very difficult from the material point of view. 2 phi f is again, if you remember, is a function of the acceptor and concentration which you have done, right, Vt ln of Na by Ni, right. Now, that means the acceptor and concentration is one sort of knob with you by which you can change phi f. The last part is Q depletion by Cox. Q depletion we have already seen in our previous example, that is dependent on many other factors, but Cox is a fact point which is oxide capacitance, depends upon the oxide capacitance thickness. Now, you see what is Cox, if you remember, Cox is epsilon ox by Tox. See, if you want to reduce Vth to a lower value, I want Cox to be as high as possible, right. If this has to be as high as possible, I need to reduce my Tox. So, this is another knob as a designer. This is another knob which is available to you, that you please try to reduce the value of Tox. When you reduce the value of Tox, you increase the value of Cox and you make the value of Q depletion by Cox go low, and therefore, your threshold voltage starts to go low. But the cost you pay for it is that you have to make your Tox small. When you make your oxide thickness small, there is a finite probability that there will be large amount of charge carriers which will be penetrating through the oxide layer. This is known as tunneling, right, and this is leakage current. So, your leakage current will increase, your power will increase. So, the cost you pay for a lower threshold is a higher power, right, and that is visible from your understanding of this subject from this case, right. So, these are the few sort of very early sort of design knobs with you as a designer to take care of a reduced threshold voltage. And now, let us look at the charge distribution in a MOS capacitor. So, I have this metal layer here, right, I have this metal layer here. So, this discussion is taken from Niemann only, right, Niemann only. There is a book by Niemann, have a look at it, for semiconductor devices. Then I have an oxide layer here. So, this is metal oxide, this is p-type semiconductor. Since it is a p-type semiconductor, it will have an acceptor ion concentration within the p-type semiconductor. I am assuming again here the oxide layers are relatively much thicker in dimensions, and the metal layer is also there. Let us go one by one and explain to you what I am trying to show to you. These blue colored squares or rectangles, whatever you see, is basically the total amount of charge which is getting accumulated because of an applied potential. Let us go one by one. If you look at the first charge, which is QMT prime, this is the metal layer charge, right, and this will be obviously there because there are large number of free electrons available in the metal, and because of that there is a charge available in the metal side. There will be also a charge in the oxide layer on the left hand side. As I told you in the previous lecture also, I am not inserting any charge into the system. So, the total charge will always be balanced. So, if you add charges on the metal and oxide side in a positive sense, you need to also add, or the system will also add a negative charge on the semiconductor side. You see, you have these blue colored charge, blue colored box here, a blue colored box here, they are both positive, and you also have a blue colored box on the semiconductor side which is negative. So, if you add these two, QMT plus QSS prime, they have to be thermally equal to QSD prime max. I will explain, and I hope you understand by this time why is it like that. This XDT is the depth of the depletion layer onto the semiconductor side. So, I have one charge which is Q prime MT, I have another charge which is Q prime SS. Q prime SS is the charge in the oxide layer which is comprising of interface trap charges, oxide trap charges, and so on and so forth. And the third charge which is in the semiconductor is basically the charge which is because of the depletion region, and this is given by Q times Na times XDT. Na is basically the charge density, and therefore if you multiply that with x dt, the distance and the q value, you get the charge, because n is a number, multiplied with q 1.6 10 to the power 19 and you get the charge. Now they have to be always equated. What will happen is, go on increasing the value of gate voltage, the metal and the oxide will increase, and therefore will the depletion thickness will go on also changing, such that the total charge thickness might reduce, but the number of charge particles might increase, fixed charge particles might increase. Takeaway from the previous discussion is that the net charge will always be the same, the total charge might vary from time to time, but the net charge will always remain the same. The second aspect was that if you want the threshold voltage to be minimum, try to make your metal and semiconductor work function as close to each other, try to make your Na as small as possible, and also try to make your Cox as large as possible. If you make your Cox large as possible, Tox has to reduce. Tox reducing means that the oxide thickness reduces, there might be current flowing through the tunneling, and there will be a leakage current available to us. So that is taken care of there. Now we come to an important parameter of a MOSFET, which is seldom used when we do a circuit simulation, especially when we do an analog design, where we want to find out, say for example, the gain of an analog circuit. This is defined as transconductance, right. Transconductance, also referred to as GM, G suffix M, right. It is basically the rate of change of the drain current with respect to the gate voltage for a constant VDS. So I fix the value of VDS, I go on changing the value of gate voltage and try to extract the value of the ratio of change in the drain current with respect to the change in the gate voltage will give me the value of transconductance. Now this is quite interesting and tells you two important points. First is, let's just deep dive into it and see, if my GM value is relatively large, it effectively means that for a small VGS change, I get a much larger change in the value of ID, which means that my device is quite sensitive to variation in VGS, So I will do a small change in VGS and I would possibly get a very large change in the drain current, right, and that is what is shown here. So the sensitivity of the device is directly related to the transconductance of the MOS device, right, and therefore otherwise is that if GM is small, I need to have a larger gate voltage for the same amount of current to be generated. Please understand, this is with the condition that I have a constant VDS with me, and therefore the sense is that typically as a designer, if you want the gain to be high, gain is basically, if you look at output voltage, is basically change in the drain current multiplied by external resistance out. So if you are able to maintain this very high, then obviously del, so this will be del V out will be very high, and that is the whole idea, that if you want a device to have a relatively a large gain, you try to ensure that del V out is very large, and therefore for a small change in the input voltage, what is the input voltage here? The gate voltage is the input voltage here. So for a small change in the gate voltage, if I get a large change in the output voltage, I define that to be as a sensitive device, or a gain is very high, right, and that is the reason we say that this is transconductance. Now if you plot transconductance with overdrive and drain current, you should know how does it behave, and therefore this slide is being discussed in order for you to understand where should you bias your device if you want the transconductance to be high. But transconductance is given by this formula here as well as this formula here, either of the two you can use it, right, and it is given by 2 ID upon overdrive, right, also given as 2 mu n C oxide W by L into ID, where ID is the current which is flowing through the device. So there are 3 plots here, look at the bottom side, this plot and this plot, right. Now let us look at this plot, this is easier to sort of understand. Obviously since GM is inversely proportional to VGS minus VTH, so GM falls in a hyperbolic fashion in this manner, correct. So for a very large value of overdrive, your GM is almost going to a very low value, and this is with the condition that ID is constant, right, this is first thing. Now the second plot of course is that this on the left hand side, the first plot you see, this is W by L constant, and my GM is following a graph which is linearly dependent on the value of the overdrive. right? I will explain. You might get confused that this is just the opposite of this one, right? So just we'll come to that later on. And if I take W by L constant, if I plot GM versus ID, I get a curve like this. So let's first take up this, and then I will try to resolve the apparent difference between these two. So it is GM versus ID, or GM with respect to ID, right, with a constant W by L ratio. Now as the ID increases, as we can see, GM is proportional to the square root of ID, and that is the reason you get a profile something like this. So if you want to operate at a higher GM, try to make your current to be also large, which effectively means that operate in saturation at a very large value of ID. The cost you pay for it is your ID square into R, which is basically the power dissipation will also increase, right. So this one is very straightforward and way to go. Let's look at this graph. Let's look at this graph. If you look at this graph, then as the VGS minus VTH goes on increasing, what is happening, I tell you, with W by L constant? If your W by L is constant with increasing VGS minus VTH, since your overdrive is increasing, you are forming more and more of inversion layer, and that is the reason GM is going on increasing with respect to VGS. So if your overdrive is 0.5 and if your overdrive is 0.8, in both the cases 0.8 will give you a much larger inversion layer charge, and therefore your transconductance will be much higher, and that is the reason you see almost a linear increase in the value of GM for a fixed W by L. However, if my ID is constant but my W by L is varying, which means but W by L cannot vary once you have fabricated it, but if my ID is constant, my drain current is constant, how do you define transconductance? It is del ID del VGS, right. Now if you look, if your ID is held constant, GM should be ideally 0, because it is del ID del VDS, but you are not changing ID, right. In this case you are changing maybe W by L, or maybe you are changing Cox or whatever, and therefore if you look at this graph is not very much utilized in devices domain. In this graph, if you look very carefully, as the and that is the reason the problem with this graph is, as the overdrive increases, therefore your transconductance shows a drop for a fixed ID, and the reason is it is mathematical in nature, there is no physical concept attached to it. So we will be therefore in all probable purposes refer to this graph and this graph for all practical purposes. I showed you this graph, the third graph, in order to appreciate the fact that if you do not consider W by L constant, you will have a problem in terms of finding out the plotting the graph. Okay, this is my last slide for this talk, and I will just quickly go through it, and then we will discuss it later on when we come back in the next class. So this is, I am plotting now a capacitance versus the voltage. We have understood threshold voltage, we have understood transconductance. Now we come to capacitance versus voltage. I will just briefly go to it and then more detail later on. This region this region is basically my inversion region, this is my flat band, and this is my accumulation. What we are showing here is, don't look at all those points and dotted line, this we will discuss later on. What we are showing is that if you vary the gate voltage from a negative value to 0 to a positive value through the threshold voltage, then how does the various components of capacitance vary, right. We will start this from the next turn onwards, right. So we will start from the next turn, give you a more basic example here, and after this we will go to second order effect of MOSFET. That will take care of the MOSFET discussion, right. I hope you enjoyed the talk. Thanks a lot.